Dear students, welcome to lecture 3 of heat transfer. So in this session, we will quickly recap some of the lecture 2 contents. So as you would recall, in lecture 1, we went over some of the basics for heat transfer. And in lecture 2, we kind of built upon those basics and entered into some complex problems. Now it's going to get a bit more complex. Okay, so we are touching upon different topics actually in today's lecture. So we will quickly recap on some important stuff we went over in lecture 2. Followed by that, we will look at conduction with internal heat generation, and we will follow that up with simple heat exchanger design that involves a concept called log mean temperature difference. We will move on to radiation topic from there, and finally try to end today's lecture or this lecture with unsteady state heat conduction. Different topics, basically there will be different topics within this unsteady state heat conduction. Right, let me try to get the laser pointer. All right, okay. So in lecture 2, we went over conduction through flat walls in series, and we also went over conduction through hollow cylinders in series. And finally, we tried to combine both conduction and convection, which is more of a realistic scenario. All right. So, irrespective of how heat transfer happens in series, so we learned that rate of heat transfer would be equal to overall temperature difference divided by summation of resistances, right? So again, this was the case where you have a flat wall through which heat transfer is happening via conduction, and either side of it there is a fluid, and the heat transfer is happening via convection on both these sides. And just to refresh, 1 by HA is resistance when heat transfer happens via convection, and delta X by K is resistance when heat transfer happens via conduction. All right, so you basically have summation of all these resistances when heat transfer happens in series. All right, and we also introduced a new term called as overall heat transfer coefficient to capture all these ways by which heat transfer is happening. Okay, so you want one term that capture how heat transfer happens when both conduction and convection are happening in series, or heat transfer is happening through both modes in series. All right, so we introduced overall heat transfer coefficient, and that was for the case of a flat wall. And similarly, we had a form for when heat transfer happens via both conduction and convection through a hollow cylinder. All right, so again the same thing. Okay, so your rate of heat transfer is given by overall temperature difference divided by summation of resistances. The only new thing has been, we have been provided with a log mean area, right? So you have two different areas, inside and outside. So log mean area was introduced, and because of the reason that we have two different areas, your overall heat transfer coefficient was also defined as inside overall heat transfer coefficient or outside heat transfer coefficient. Okay, so you can rewrite this form with either UI or U naught. Okay, so we have seen a problem where you solve it either this mode this way, or you solve it using overall heat transfer coefficient. You should end up getting the same rate of heat transfer. I think you guys are all good until so far, right? Okay, so Sorry, this was supposed to be a recap of lecture 2 again. Okay, so we are in lecture 3. All right. Okay. So from there, we will move to a different scenario. So what if conduction is happening with internal heat generation? All right. So let's consider this slab shown over here, where heat is being generated within at a rate of q dot. Okay, so this is heat generated or rate of heat generation per unit volume. Okay, so some practical scenarios would be, for example, if a reaction is happening within a slab and heat is being generated due to the reaction. Okay, that's happening. Or you can consider nuclear rods, for example. All right, so they are hot. Okay, so okay, so those are such examples. All right, and let's assume that at the end of the slab or at the wall. Okay, so the temperature is at TW, it's at a constant. All right, and we also know that the temperature at the center is T naught. All right, and we want to come up with an equation that will provide the temperature profile, okay, within the slab. Okay, so we want to know the temperature at any location. Okay, so at any location within the slab when heat generation is happening within inside. Okay, all right, so how do we do that? Okay, so we start with heat balance. We consider a small unit volume of thickness delta x and area cross-sectional area A, and the heat in plus heat generated within would be equal to heat outside. Okay, heat outside that unit volume, right? So similar equations you must have seen in momentum transfer. All right, so throughout your transport phenomena, we will try to develop mathematical models from this one line of either balancing momentum or heat or your mass. Okay, so in this case, we are doing a heat balance. Okay, so we call this as a heat balance. Okay, heat in plus heat generated is equal to heat that comes out of that unit volume. Okay, so in this case, there is no heat accumulation. That's why we have it as 0. Okay, so rearranging it, so we get to this form. Okay, so you go to the basics of your derivation, then you will see how we got dq by dx, right? And within here from Fourier's law, we know what Qx is. Okay, so Qx is minus k dt by dx. All right. Okay, so you have a negative sign to indicate that heat flows in the direction where the temperature is going down. All right. Okay, so that's the reason you have a negative sign. All right, so you substitute qx into this equation, so you will get a second order differential equation with, after solving. Okay, so you will have two constants, right? Whenever you solve a second order differential, okay, so you will have two constants. All right, and this is an important concept as you learn. Okay, so heat transfer, and basically you are learning, or basically we are providing few lectures in heat transfer so that you can transition to advanced transport phenomena. Okay, graduate level advanced transport phenomena. And in there you would see that we will derive some models which has constants, and we will apply boundary and initial conditions and solve it. All right, okay, so now, okay, so this is one such example. All right, so you obtained a second order differential, and upon solving it you end up with an equation having two constants. And how do I solve for these constants? Okay, so we'll be applying boundary conditions. All right, so what are the two boundaries we know of? We know that at x is equal to 0, t is equal to t naught. All right, so you can substitute that. Okay, so let's say for example, okay, at x is equal to 0, this term would get cancelled, this would get cancelled, and we know that at x is equal to 0, t is equal to t naught. So basically c2 is equal to t naught. All right, so we solved for c2. All right, so that's substituted here. And likewise you can solve for c1 by substituting at x is equal to L, t is equal to tw. All right, so try to substitute at x is equal to L, t is equal to TL, and we also know that C2 is equal to T naught, right? So with that, solve for C1 and substitute both C1 and C2, then you will get an equation. All right, so this equation actually here is incomplete. If I was working out, if I was giving this lecture in the class, so I will usually have a docam and complete this part with a C1. Okay, but I think you guys are in grad school, so you should be able to solve this on your own. Okay, so this is incomplete, only C2 has been entered here, so you should complete it by calculating what C1 would be with the second boundary condition I spoke about. All right, so again, this is a very important concept. Okay, so we're learning how to identify boundary conditions. Okay, so for this case over here, the boundary condition is at x is equal to 0, t is equal to t naught, and at x is equal to L, or in this direction as well, at x is equal to L, t is equal to tw. All right, so using that you can solve for the two constants and substitute into this equation, and you will get an equation with which you can get the temperature profile, right? So basically, yeah, with this equation only t and x are unknown, so basically, yeah, substituting any value of x, I can get to know what is temperature, right? So everything else is known. I know q dot, I know what thermal conductivity, I know T naught. Likewise, when you substitute for C1x, you will see that everything within C1 is of course a constant, and only x is known, right? By substituting x, I'd be able to get what is T. Okay, so that was the goal, right? Okay, now let's change topic a little bit. Okay, so let's move on to log mean temperature difference. Okay, so this concept occurs when we try to design this simpler heat exchanger called as a double pipe heat exchanger. Okay, so this is the simplest heat exchanger one can imagine. So where you have an inner pipe and you have an outer pipe, right? So we use this either to heat a fluid or cool a fluid. Okay, so for example, you can have steam flowing through this inside pipe, and you can have an oil flowing through the outer pipe, and you would want to heat the oil, for example. Okay, so say for example, before the crude oil gets into the distillation column, I want to heat it up to a certain temperature, right? So I can use a heat exchanger for that purpose. Okay, so you can do that. Or for example, okay, so at the top of the heat exchanger, all right, so where the vapor comes and I would want to condense it, right? So I could have the vapor flowing through here, and I can have a cooling liquid, okay, a coolant liquid flowing through the outside tube. Okay, so that cools down the vapor. So different purposes. Okay, this is a heat exchanger, and as a person who is learning heat transfer, the goal is to identify what is the surface area needed to cool or to change a fluid's temperature, say for example from T in to T out. Okay, so what is the size of heat exchanger needed for that purpose? All right. Okay, so the temperature profile for such a scenario would look like this. Okay, say your hot fluid, it enters at T1 dash and it exits the heat exchanger at T2 dash, right? And your cold fluid enters the heat exchanger at T2 and it warms up and enters the heat exchanger at T1. Okay, so as you know, heat is being exchanged between both these fluids. Okay, and now refresh on the earlier concept. So why is heat transfer happening between both the fluids? It's because there is a delta T, right? So there is a driving force. Whenever you have a driving force, a temperature difference, then heat flows, thermal energy flows, right? Thermal energy flows from one fluid to the other, from the hot fluid to the cold fluid. Okay, but the problem here is that this driving force is not constant. It varies throughout the length of the heat exchanger. Okay, so it varies throughout the length of the heat exchanger as shown over here. All right. Okay, so just remember that. Okay, and I will switch to a slightly different concept but associated with the heat exchangers. The double pipe heat exchanger that we are discussing here, it can either be designed as a counter current heat exchanger or a co-current heat exchanger. All right, so this is the temperature profile for a counter current heat exchanger where both fluids are flowing in opposite direction, as you can see by the sign of the arrows. And we can also have a co-current heat exchanger where both fluids are flowing in the same direction. Okay, so as the arrows are indicated. But irrespective of the type of the double pipe heat exchanger, delta T actually varies. All right. Okay. So from our basic form of Q, we know that Q is equal to UA delta T. If somehow we can come up with a mean delta T, all right, and by knowing U, which depends upon heat transfer coefficient of this fluid, heat transfer coefficient of the fluid, and then the thermal properties of the pipe that comes in between, by that you will know U, then I can calculate what is the area required. Okay, so that's where log mean temperature difference comes into picture. Okay, because your delta T is not constant across the double pipe heat exchanger. All right. Okay, so there is a long derivation for it. Okay, so you can, if you're curious, refer to Giancopoulos and you can see the derivation for log mean delta T. All right, so basically, yeah, you obtain delta T at both ends. Okay, so for this counter current heat exchanger, on one side you get delta T1 and on the other side you get delta T2. You write down log mean temperature difference for that. Okay, so this is the form for it. Okay, so by substituting in here, okay, so as I said before, if I know U, then if I also know how much Q needs to be exchanged, then I can find out the area required. All right, so typically, yeah, we know that. Okay, so I would want to heat a fluid, or I would want to cool a fluid, say from T1 dash to T2 dash, right? I would know that. Or if a crude oil is at room temperature, and I know that I would want to heat it up to say 80 degrees centigrade, I would know that, right? And coolant liquid will be entering at T1 dash, and by utilizing energy balance I can calculate what T2 dash would be. All right, so there will be example problem in the book where you can find out. Okay, so using the heat balance using MCP delta T equation that you learned before. You can find out the fourth missing temperature. Once the fourth missing temperature is known, you can find out both these delta T's and calculate log mean temperature difference, and you can solve for the area. All right. Okay, so this is the concept of log mean temperature difference. Okay, so the same formula applies for both countercurrent as well as co-current heat exchanger. Okay, please refer to the book to see how this formula is applied to design the heat exchanger. This is the simpler heat exchanger. Okay. Okay, oh, okay, so I do have a problem over here, but yeah, um, I will, give it a second so you can pause and read the problem statement and, practice it on your own. It's similar to, what I said. Okay, so for one fluid, both temperatures are provided. Okay, so, okay, so for T1 and T1 dash are provided. Okay, or okay, so outlet T1 is missing. Okay, so other T2 and T2 dash are provided, T1 dash is provided, T1 is missing. Okay, so you can do a heat balance for one of the fluid. Okay, so the one which has T1 dash and T2 dash, right? So for that you can do a heat balance and find out how much of energy is being um, utilized to cool down that fluid for this case. Okay, so how much of energy needs to be lost by that fluid, that can be found out. Okay, so you equate that to the other fluid, and you can find the missing temperature. All right, so with all those temperatures known, you can calculate log mean temperature difference, and you can substitute into this form and calculate area. Okay, so I kind of went over it a bit fast. Okay, because we need to touch upon different topics. Okay, but take some time and try to understand the problem statement carefully and solve it on your own and practice it on your own. All right, so we will switch gear. Okay, so we have seen how you would calculate heat transfer rate when heat transfer happens via conduction, and we moved on to convection, and we also try to couple both. And there is a third mode by which heat transfer happens, which is radiation. And it's not very commonly used for designing unit processes in industries, and for that we typically don't go over this in too much detail. But as students who are graduating with ChemE, you should know something about radiation, right? So I'm just giving some glimpse of it. And as we have seen in the first class, radiation is when energy is emitted by matter due to changes in electronic configuration of its atoms or molecules, and this energy that is emitted is transported as electromagnetic waves, and for that reason, okay, so no physical media is required. Okay, and we are going to see what is a mathematical form which describes the rate of heat transfer via radiation. All right, so some of the properties of radiation. So whatever properties you know about electromagnetic waves applies for radiation as well. Okay, so it's going to travel in straight lines pretty fast. Okay, travels through vacuum, and that's why if you're getting energy from sun, okay, so it travels through vacuum. All right, so radiation properties. Okay, so radiation energy can either be absorbed, and we indicate this term by absorptivity alpha, or radiation energy can either be reflected, which would be reflectivity, and radiation energy can either be transmitted. Okay, so basically if radiation falls on an object, it can either be absorbed or reflected or transmitted, right? So this is basically the fraction of energy that is absorbed that's absorptivity, fraction of energy, that's reflected, reflectivity, fraction, that's a transmitted, that would be transmittivity. So when you sum up all those fractions, it should be equal to 1. Okay, so radiation energy, I does either of these three. Okay, so it should be 1. Okay, and in engineering cases, okay, so your transmit is equal to 0. All right, so the objects that we are dealing with, they are not transparent, to put it simply. All right, so for that reason transmittivity is going to be equal to 0. All right, and we are going to define a concept called as a black body, for which reflectivity is going to be equal to 0. All right, so we already saw that, transmittivity is equal to 0 for most engineering cases, and when you have reflectivity as well equal to 0, then alpha becomes 1. Okay, so for a black body, alpha becomes 1. Okay, so this is kind of an ideal scenario. So imagine a sphere, and it's the inside is coated with something black. Okay, so which is going to absorb light that falls on it. Okay, and there is a single tiny hole through which light enters, and what would happen to this light is, or a thermal energy that comes in due to radiation. Okay, so it travels through this tiny hole, and just within this body. Okay, so all the light, okay, so it reflects and finally it dissipates. Okay, so everything gets absorbed. All right, so this is an example of an ideal black body. So because nothing comes out of this ball, okay, so everything is being absorbed, then we say the alpha for black body is equal to 1. Okay, now we introduce a new term called as emissivity, and emissivity is a ratio of emissive power of any surface. Okay, so for which we are interested to know what its Q is going to be to that of a black body. Okay, right. Okay, so emissivity is a ratio of emissive power of a surface to that of a black body. But if you compare emissive power of black body to that of a black body, it's going to be 1, right? Obviously, so emissivity for black body would be equal to 1, right? So knowing this, so there is a law called as Stephen-Boltzmann's law, using which you can calculate rate of heat transfer via radiation, which is given by A epsilon sigma T to the power 4. Okay, and T is the temperature of the surface, for which I would want to know what is its emissive power, right, or the heat transfer rate via radiation. Okay, so A is the surface area of that surface you are interested in, and epsilon is the emissivity of that surface. All right, and the sigma is a Stephen-Boltzmann constant, which is shown over here. So by knowing temperature and emissivity of that object you are interested in and the area, you can calculate Q basically. All right, so we will stop here for radiation. Okay, so just want to give you guys a glimpse of radiation. All right, let's move on to unsteady state conduction. Okay, so until so far, all the conduction cases we have been dealing with are a steady state. Okay, so in particular to heat transfer by steady state, what we mean is the temperature doesn't change with time. Likewise, Q doesn't change. Okay, so when we have objects in series, okay, so Q from A to B, okay, they are all equal, right? We have seen that. Okay, and throughout as well, Q doesn't change. All right, and unsteady state heat conduction is important in some process industries as well. Okay, so some examples are shown over here. Okay, so say for example you want to cool a metal rod, or in food industries. Okay, so meat sausage is being cooled. All right, so or you are freezing packages or baking. All right, so the temperature is changing with time in all these examples. Okay, so you do want to know unsteady state conduction, or you should be able to develop equations for unsteady state conduction and calculate the temperature that is needed to cool down an object from a certain temperature to this, or heat an object from a certain temperature to a very high temperature, right? So those are all unsteady state processes. Okay, so we should know unsteady state conduction for those reasons. Okay, and so you will see that when you move on to advanced transport phenomena, we will consider an unit volume, and we will do a balance across this unit volume and come up with equations. Okay, so we did look at such an equation previously as well. Okay, so basically across this unit volume, rate of heat in plus rate of heat generated within this unit volume would be equal to rate of heat output plus rate of heat accumulation. All right, so with that, okay, so you will come up with this general form for unsteady state heat conduction. So you will look at these repeatedly in your advanced transport phenomena. Okay, so you would spend some more time getting into this, but I just want to give a glimpse of this equation, okay, for you to familiarize with this equation. All right, so you can see here that unlike the Fourier's form you saw previously, you didn't have a time variable in there. Okay, but this is a partial differential equation where temperature changes with time as well. Okay, so you have that. Okay, and then we also introduce a new term called as thermal diffusivity. This kind of talks about if I consider an object, how fast thermal energy dissipates from that object, right? So your thermal properties dictates that. Okay, so for example here, okay, so your K thermal conductivity talks about how fast heat would be transferred, okay, or a CP, okay, so which is um, which also talks about how much heat it can hold, right? Okay, so therefore, okay, so we would want to develop one term that captures everything together. Okay, so we have this called as thermal diffusivity, right? Okay, so alpha stands for thermal diffusivity. We have the thermal conductivity at the numerator, which means that as the thermal conductivity increases, thermal diffusivity is also going to increase, right? And likewise you have a CP in the denominator, right? So if a CP is high, okay, so the amount of heat that body can hold to raise its temperature per Kelvin, okay, so that is going to be much high. Okay, so then thermal diffusivity is going to be lower. Okay, so it's inversely proportional to thermal diffusivity, so therefore it makes sense. Okay, so what you see here makes sense. All right, okay, so just remember, okay, so this is a new term, okay, that captures okay, thermal diffusivity. All right, K alpha is equal to K by rho Cp. All right. Okay, so before we move on to the next topic in unsteady state heat conduction, we'd want to introduce a new dimensionless number called as Biot number. I think you should have been introduced a dimensionless number called as Reynolds number in momentum transfer or fluid mechanics, right? Okay, so now we are going to introduce a new number called as Biot number, all right? Okay, so in all these cases of unsteady state heat transfer, okay, so the examples we saw, we have some material that needs to be heated or cooled, right? So energy is going to get transferred from that material via conduction to the surroundings via convection, right? Okay, and at that instant, heat energy that is being transferred via conduction within that material would be equal to heat energy that is transferred via convection, right? And if we consider this material's temperature at either ends to be at TS1 and TS2, and since we are talking about unsteady state, okay, so this TS2 changes, okay. So irrespective of what TS2 is going to be, the rate of heat transfer at that moment via conduction would be equal to rate of heat transfer via convection, right? So we have seen what is rate of heat transfer via conduction previously, which is delta T by delta X by K. That's what has been written here. Delta X here in this case is L. Okay, so that's what you have, would be equal to heat transfer via convection HA into delta T. So the temperature difference in the convection scenario is TS2 minus the atmospheric temperature T infinity TL. All right. So you rearrange this such that you have both deltas on one side, and what you end up having is resistance due to conduction 2 divided by resistance due to convection on the other side. Okay, so this term, okay, so this term dictates how this slope is going to be, right? So how this slope is going to be, whether heat transfer via conduction or whether heat transfer via convection is the one that is controlling, okay. So which is going to be dictated by this term, and now we call this ratio as the Biot number HL by K. All right. So we have this dimension L for a flat slab. To generalize this Biot number, we introduce x1. Okay, so x1 stands for characteristic dimension. So we have this characteristic dimension for any geometry, let it be a cylinder or a sphere or a cube, etc. Okay, so you can refer to the book. Okay, so basically, yeah, what you would want to know is this Biot number provides the ratio of conduction resistance to convection resistance, and looking at the Biot number, I would know which either conduction or convection is controlling the heat transfer in that particular scenario. Okay, so that's the significance of Biot number. Okay, so let's move on to simpler and steady state heat transfer, so which is called as lumped capacitance method. Okay, so this method can be utilized when Biot number is less than zero point 0.1. So what does that say? So we know that Biot number is ratio of conduction resistance to convection resistance. So when Biot number is very, very low, it means that conduction resistance is very small. Conduction resistance is negligible. Okay, so there is no resistance to conduction at all. Okay, so whatever resistance to heat transfer you see appears due to convection. That's what it says. Okay, so there are practical scenarios where this is valid. Okay, so for example, you consider an object, you consider a very hot object at temperature T naught. It is dropped to a vessel with a fluid T infinity. All right, it's dropped to a vessel that has fluid at T infinity, and this object can be a metallic bead. Okay, so metals have a very high thermal conductivity, and for that reason you can assume that temperature within any point of the metal is the same. Okay, so temperature doesn't change with dimension, but because it is in a fluid, temperature changes with time. Okay, so that's your lumped capacitance method. You have a metal with a very high thermal conductivity. All right, so when your thermal conductivity is very high, Biot number becomes low, right? Okay, so for that scenario, okay, So you could assume that, temperature across that material is uniform. There is no change in temperature within that material. Okay. And so you're basically lumping the temperature as just one temperature for that material. Okay. So temperature for that material changes with time, irrespective of the location. All right. And we would want to develop an equation to capture this temperature of the material at any time t using lumped capacitance. Okay, so we do a heat balance. All right. So heat transfer that happens via convection. Okay, so heat transfer that happens via convection from that material to the surroundings T infinity, and you multiply by the small time interval through which this heat transfer happens. Then you get your energy that was transferred, and that energy would be equal to the energy the that this material would release when its temperature changes by dt, small temperature dt. Okay, so which would be equal to cp rho v. So basically you get this from emcp delta t. Okay, so emcp delta t, where em is nothing but rho v, right? So heat energy that this material loses, mcp delta T, would be equal to the heat energy absorbed by the surroundings. Okay, and you integrate it from time t is equal to 0 to time any time t. All right, and at t is equal to 0, the temperature of this material is T naught, and at any time T, we do not know what its temperature is, so we give this variable T, right? And you solve for it, and you get this equation with which you can, calculate the temperature T for any time T. Okay, so this equation you can apply for the cases when Biot number is less than 0.1. Okay. All right. So let's move on to unsteady state conduction for a flat plate with negligible surface resistance. Okay, so we will look at two more unsteady state heat conduction scenarios. We will see how the starting a partial differential equation would look like, and the learning concept here would be about your initial condition and the boundary condition. Okay, so for all these cases you will learn how initial conditions and boundary conditions would look like, and that's what you would be utilizing in your advanced transport phenomena. All right. And for this case over here, so this flat plate is at a temperature T naught at a time T is equal to 0. All right, so it's at a certain temperature T naught, and it is subjected to surroundings. Okay, so at time greater than T is equal to 0, it's exposed to surrounding temperature of T1. But for this case, you assume that the surface resistance is negligible. Okay, the convective resistance is very small, and therefore the surface of this object also has the temperature of the surrounding. Okay, so because there is no surface resistance, no convective resistance, the temperature at the surface is equal to that of the surroundings. Okay, at any time t. All right, so let me see. So basically, yeah, when you expose it to surroundings of a temperature T1 from this T naught, it would, at the next time T, okay, so a profile like this will be, sorry, my drawing isn't quite good. Let me clear this. Okay, so you will okay, so you would see that temperature is slowly dropping. Okay, so like this. Okay, so at different times t, it will keep on dropping, and at a very long time t. Okay, so it would approach this flat line of t1 basically, right? So you would want to get an equation for this temperature profile. Okay, so where temperature not only changes with x, but temperature changes with time as well. All right. Okay, so let's see how to do that. Okay. Or how. Okay, let me erase it. Okay. So, or how we do it in transport phenomena. All right. Okay. All right, so we start with our general equation for unsteady state heat conduction. We saw earlier, okay, so this is simplified because there is no heat generation within this object. And okay, so it's a second order differential equation, partial differential equation, and you solve it by utilizing initial condition and boundary condition. Okay, at t is equal to 0 at any x, this is your initial condition. We know that t is equal to t naught, right? Initially t is equal to t naught, and at any time t within the boundaries at x is equal to 0, so which is at x is equal to 0 or at x is equal to 2h. Okay, so at two different boundaries you have temperature is at T1 for this case. Okay, so you have both the initial condition and boundary condition. So with that you can solve this equation as we have seen previously. Okay, and a new concept. Okay, so in transport phenomena, you would see that the variable for which you are trying to solve, we will define a dimensionless term. Okay, so for this case, okay, so we are trying to obtain an equation for temperature. We introduce a dimensionless temperature. Okay, such that, okay, so it varies from 0 to 1. Okay, so that it can be generalized. Okay, so we define a dimensionless temperature. You see that t is the variable, otherwise t1 and t naught are constant. And as you substitute it, okay, so it could either be a t1 or a t naught, right? So when you substitute t1, then this becomes 0. You substitute t naught, it becomes 1, right? So your y varies from 0 to 1. Okay, and therefore your initial and boundary conditions also varies from 0 to 1. Okay, so you can substitute these and solve that equation using a method of separation of variables. And initially you get this equation with a and b as constant. Okay, so you can apply your boundary condition, solve for a and b, and you get this analytical solution. All right, where you can substitute any time t at x that you are interested in, and you can get your temperature. All right, so this is your analytical solution for this case, second case of unsteady state heat conduction. And let's move on to a final case of unsteady state heat conduction involving a semi-infinite solid. Okay, so what this could be, for example, your Earth, which is at a temperature of T naught, okay, at time t is equal to 0. So therefore, when you consider Earth, okay, so it's infinite in the direction of its depth, right? It's infinite. You can assume that it's infinite depth, right? And it's suddenly exposed to a temperature T1. Okay, so your Earth is suddenly exposed to a temperature of T1. And in this case, okay, so unlike the previous case where we assumed negligible resistance due to convection, okay, so that can happen when H is very large, right? When H is very large, there is no convective resistance. Then your surface is also at the same temperature as the atmosphere T1. Okay, so now over here we are looking at a different case where H does exist. Okay, in a practical scenario, it cannot be too high that this can be neglected, right? So then compared to your surroundings, there will be a temperature drop at one of the boundary, at this boundary. All right, and we start with our general equation for unsteady state heat conduction. and we utilize the boundary and initial condition. Okay, so we just saw that the initial condition is at ex is equal to, or sorry, at t is equal to 0. Okay, initial time t is equal to 0, temperature is equal to t naught. Okay, so we saw that. Okay, at t is equal to 0, t is equal to t naught, and that's your initial condition. And the boundary condition is going to be at any time t at the surface at x is equal to 0, heat transfer that happens via conduction would be equal to heat transfer that happens via convection. Okay, so that is one of the boundary condition. And at x is equal to infinity, the other boundary. Okay, so you assume that, okay, so the initial temperature would still remain at any time t. All right, so using that we get this analytical form. Okay, so you will see that we wouldn't actually use these analytical forms to identify to solve for temperature, but we will be using a plot such as these. All right, so just want to give you all a glimpse of it. Okay, so in undergraduate class for different geometries we would be using different plots such as this to calculate the temperature T for different times t or at any location x. All right, okay, and within this analytical solution you have c, which is 1 minus error function. Okay, so you can google for it and see how an error function would look like. Okay, so with this I would want to end lecture 3. So we went over several topics in lecture 3, and I hope it wasn't enough time, but I was able to convey what needs to be known. Okay, so within this short time. Okay, so you can pause and go over the slides once more and refer it along with the book and to learn it more deeply. All right, so thank you. See you all in lecture 4.